Hi. Last time we were discussing the Wedderburn-Norton theorem, and we made a head start toward proving it by proving first that a ring, which is a semisimple right arm module over itself, has all right modules semisimple. Now the converse of this assertion is also obviously true, so we have the equivalence that you see in the slide. The next thing we're going to do will be to discuss the important features of a semisimple ring, namely a ring that is semisimple as a right module over it. And the very next thing, the very first thing we will do next is to discuss the module analog of what is known as the Frattini subgroup of a group. The Frattini subgroup of a group is simply the subgroup of that group generated by all the elements called non-generators. Here we give a definition of a non-generator. Take a group G, capital G, and take a lowercase g, which is an element of G. Then that little g is called a non-generator if it can be excluded from any generator subset of G containing it, in the sense described in the definition. So, for example, every element of the group of rational numbers is a non-generator, which would be a fun exercise to show. Therefore, Q is its own Frattini subgroup. Now, how does the module analog go? Well, the next definition may not be what you immediately expect to see. So, let's give it. Well, take a module B and a submodule A. Then A is said to be small in B if the sum of no proper submodule with A is equal to B. That means B is equal to C. Okay. So if whenever A plus C is B for a submodule C of B, then this will imply B is equal to C. I think this is a very aptly given name to such a submodule as A. It is so small that it never complements anyone to the full module B. Well, it is this form. So what does it have to do with the non-generators? Let's clarify that. Well, this will be easy to see. Then every non-generator element generates a small submodule of B. In fact, they are precisely those elements that generate small cyclic submodules of B. It's not hard to see the connection. Once again, we give our example of rational numbers, but this time as a module over the ring of integers. So every proper submodule of Q as a Z module is small. Okay, next we are going to give a lemma that will facilitate the proofs of some of the results that we want to do toward the proof of the general theorem. So it is this lemma. It says that the smallness of a submodule is preserved under module homomorphisms. So you take a homomorphism F from a module M into N and a small submodule A of M, then its image is again a small submodule of N. Let's prove this. Okay, so first assume that the sum of F of A, the image of A under F, with a submodule, say C, of N is equal to N. We want to prove that C is equal to N. Okay. Now, since F may not be onto, here's what we're going to do. First, we will intersect the whole image of F with both sides, and we get this second line here. By modularity, of course. Now, we did this because in order to pass to the module M without losing anything in the sum, we needed to have everything contained in the image. So it's an easy exercise to show now that when you apply F inverse, when you take the inverse image with respect to F of both sides, the inverse image distributes over the sum on the left side of the equality, as you see on the last line. Well, the last line is equal to, well, the last line can be paraphrased by saying that A plus kernel F. So where do I get this? This is F inverse of F of A. So A plus kernel F plus the whole, I took the whole thing without changing it, F inverse of C intersect image of F, that's equal to M. Okay, now here's what we're going to, okay, now here's what we're going to do next. The kernel F, oops, sorry. The kernel F is actually contained inside this term here, so it can merge in it and give us A plus F inverse of C intersect image of F equal to M. But then we know that A is small in M, therefore this implies F inverse of C intersect image of F is equal to M. Oops. Okay. Now, this time applying F to both sides of the last equality we get, we have C intersect image of F equal to image of F, showing that the image of F is contained in C. But then let's go back to what we had at the beginning. Part of the image of F and plus C is equal to all of N. Since C now contains the whole image, then this C plus F of A, C actually swallows F of A too, so C plus F of A is simply equal to C, and that's equal to N, as desired. This concludes. Now, next thing we'll do is again prove a module analog of something, namely the fact that, the well-known fact that the Frattini subgroup of a group actually coincides with the intersection of the maximal subgroups of a group, of that group. Maximal submodule being maximal among the proper subgroups of the group, the mentioned group, with respect to, ordered with respect to inclusion. So the module version will look something like, so here's a definition plus lemma. Take a module M. We define the Jacobson radical of the module M, denoted by rad M, to be the intersection of all maximal submodules, assuming of course that they exist, and if they don't exist, then we will simply define the radical to be, okay, define the radical to be all of M. So kind of fitting the scheme where we assume that an intersection of an empty family is simply the whole module. Okay. Remember, an example, a good example is always the rationals. So the radical of Q is vacuously equal to Q itself because it doesn't have any maximal submodules. Or Q as a group doesn't have any maximal subgroups. Let's give another example for a change. The radical of the Z, the module Z over itself as a ring, is 0. and for example the radical of the 2 by 2 the ring of 2 by 2 upper triangular matrices over a field F as a right and as a left module is this right left corner here being F. So of course we are still continuing. We have only given the definition part of the definition plus lemma, and we are yet to give the lemma part of it. So let's mention that too. Well, the lemma part says that the radical of M is the sum of the small submodules of M. Well, let's recall what we said a couple of pages ago. See, here, right here in this sentence, we say A is a non-generator if and only if AR is a small submodule of B. It's actually if and only if. And which we will prove in the module case. So what we are saying is simply that the radical of M is the sum of small submodules or small cyclic submodules of M. So let's prove this. Okay, now we give a sketch of proof. To prove the inclusion of the right side in the left side, then take a small submodule, B small, in M, and notice this. If there are no maximal submodules of M, then the radical is simply defined to be all of M. Therefore, A is contained in M vacuously. So we will simply assume that there are maximal submodules, and N is one of them. If A were not contained inside N, then we would have A plus N properly containing the maximal submodule N, which would force the sum to be equal to M, contradicting the smallness of A. So here's the contradiction sign. So A is in N. This proves the first inclusion. As for the next one, so take an arbitrary element A from the radical of M. So it will suffice to show simply that the cyclic submodule generated by A is small in M. If it is not, were it not, then there would be some submodule, say X of M, which is proper and whose sum with AR is equal to M. But then this would imply that the set of such submodules as X is non-empty. The part of the proof I will leave to my viewers is to show that gamma is inductive, namely Zorn's lemma is applicable to it, and thus by Zorn's lemma we can find a maximal element inside gamma. Now we'll simply call it D, our choice of the maximal element in gamma. So the viewer should prove that D is in fact a maximal submodule. But one that does not contain A. So this poses a contradiction because we picked A from the radical. So A is small. and thus AR is contained in the radical. AR is contained in the sum of the small submodules. As desired. So this completes the part of the proof, no, the whole proof. Okay, now we give some useful corollaries to the above two lemmas that we have proved. Well, the first corollary is, well, it says any module homomorphism carries the radical of the domain module to the codomain module's radical. So radicals are invariant under homomorphisms in particular. We'll prove this in a moment, but let's show another corollary that's immediately available to us. I think it's actually a corollary of the corollary. So it says that the radical of any ring considered as a module over itself is an ideal, a two-sided ideal of R. Now this may be interesting, and this is very useful. So let's prove these things. So now the image of the radical of M under F is equal to F of the sum of small submodules of M. Now homomorphisms can factor over sums, therefore it goes like this, A small n. Okay, so now the rest is easy because we have proved already that the images of small submodules are again small, therefore we have the inclusion small submodules of in the small submodules of n, and that by the other lemma we proved is equal to the radical of n, therefore the radical of m is mapped into the radical of n by f. So this proves the first thing. As for the second assertion, now let's give a name to the radical of R as a right module over itself, call it I, and take an element x of R. We already know from its construction that I is a right ideal, because it's a right R submodule of R, and all that remains to prove is that it stays invariant under multiplication by elements of R on the left. So take an element x of R and recall that multiplication on the left by an element of R, in particular x, constitutes an R linear map from R into R as a right module. Therefore the xi, namely the collection of all products formed by multiplying x and an element of I, is simply the image of I under this R linear map. And being a R linear simply means a modular homomorphism, so being a modular homomorphism, it preserves the radical. Namely, it takes the radical into the radical. So we have the following. So we have xi contained in I. This proves that it is an ideal. So this ends our video. Thank you.